Okay, so let's go ahead and walk through this virtual lab together. We're going to be answering these questions. How does pressure change when you change the number of moles? If the volume is fixed or stays the same, how does the pressure change the temperature? If the temperature is increased, so kind of starting to look at these gas laws from a relationship from the 4 variables that we wrote down from the first video. And what does the graph look like when you change the volume? What is the graph telling you? We're actually going to create those graphs, so we want to make sure we have our notebook ready and available. And then we'll talk about the equation briefly, but we won't get into the equations too much until the next time that we are together. So in the simulation that you have here, we are going to be looking at the Explore tab so that we can explore those questions. So if you want to go ahead and open it on your screen, you can, or you can just go back and forth with us. I am going to go back and forth between the tab with the questions, okay, and the tab with my simulation open here. So our first question, how does the pressure change when you change the number of moles? Well, we got to have some moles. So I'm going to lift up my pump in some atoms. We know that atoms are an amount. We don't actually have a number of moles on this simulation, but we can see, all right, let it find its equilibrium. We can see the pressure right here is at about 11-ish atmospheres. What happens if we add a bunch more? Okay, so we can see that pressure rose a whole lot. Let's go into our notebook and let's make kind of a visual for our pressure in moles. So I'm going to go ahead and write pressure in moles. And I'm not going to actually put numbers on my graph. I'm just going to make kind of a generic graph. I'm going to put moles on the x-axis, and we'll put pressure over here. We don't even need units for our relationship graph, for our generic graph that we have here. So if we go back to what we had in our simulation, I can just keep putting in moles, and what happens? The pressure just keeps going up. So if I started here and I have more moles, then my pressure is going to be higher. So increase of moles, increase of pressure. This is what my graph is going to look like. So I might even write with more moles, with more atoms, molecules, we could use that word, since that's what our simulation looks like, the pressure increases or goes up, whatever is easier for you. So we might remember from way back when we first talked about moles, a lot of times we use the letter N to represent moles. So we could write N goes up, P also goes up. Okay. These arrow relationships will help us as we answer questions and move on to the actual laws that we're looking at. All right, so that's question 1. If you we're looking at your questions, how does the pressure change when you change the number of moles? We had, as the moles go up, the pressure goes up. What if we take away, we let out some gas? So if we let out gas, what happens to the pressure? It goes down, right? All right. So let's look at our second question. If the volume is fixed or stays the same, how does the pressure change when the temperature is increased? All right, so this time let's go ahead and set up what we're going to write here. If the volume is fixed, how does the pressure change? So we're going to say volume constant or fixed So we're going to compare pressure and temperature. Okay. So we'll have a graph. Okay. We'll do the same kind of generic relationship graph with no numbers. Okay. So I have a bucket here and it says heat and cool. So I'm going to raise the temperature and notice I can, in my simulation, I can see that temperature is rising as we look at the top of it. What is happening to the pressure? Oh, I lost my lid. Use the terminology. I flipped my lid. So if I put in some molecules, notice my temperature's at 300. Okay. They're just happily moving around. If I add temperature, if I add heat, what happens to my pressure? It keeps rising. It keeps increasing. So how are we going to show that on our graph? My temperature started here and it was over and it went up. My pressure started here and it also went up. So our graph, again, is a positive correlation. So we could even just shorten this and use our temperature goes up, pressure goes up. Okay. So this is a direct relationship. They do the same thing. And so that's question 2. If you're answering in your text entry, what happens when we compare pressure and temperature? When temperature goes up, what happens to pressure? It also goes up. All right. So we'll look at number 3. Some of you are typing. Okay. And this one, number 3, says create a graph to compare volume and pressure. What is the graph telling you? And then they want you to create a graph with temperature and pressure and moles and pressure. Well, on this, if we look at our volume, we change our volume, so our amount of space, let's return our lid. Our volume is small now. Our volume is big. What happens to our pressure? Decreased. So when volume got bigger, our pressure got smaller. If volume gets smaller, let's make it smaller, what happens to our pressure? It increases. So let's create that graph. We do not have a graph with volume and pressure yet. So we'll say volume versus pressure. Did we do anything to the temperature on this one? No. So we could even say temperature constant or temperature not changed by us. Okay, so volume and pressure. We'll have our generic graph. And we'll just keep pressure over here like we have been. This is a little bit different graph. Okay. When my volume was really big, my pressure was low. But when my volume, we'll come back to this, when my volume was really small, what was up with my pressure? It was really high. So this time, and you cannot see what I'm drawing. So this time, if our pressure is really high when our volume is really small, our relationship goes the opposite way. Okay, so when volume went down, then pressure went up. And you could write it just for clarity. When volume went up, pressure went down. Looking at what we did we ever add atoms in this scenario? No. So we need to probably make sure that we write that. No moles added. Okay. All right, so let's look at our question. We were trying to answer these questions. Create a graph to compare volume and pressure. What is the graph telling you? Well, if we go back to our camera where we did that, the graph is telling me that when volume goes down, pressure goes up. When volume goes up, like we come across the x-axis, when volume goes up, pressure has come down. Okay. All right, so you could go ahead and answer in temperature and pressure. We already have a graph for that. Temperature and pressure. We already have a graph for moles and pressure. Okay. See if I can get them all on there. And so you have all three of those that you could go ahead and answer number 3. Maybe a couple more seconds on that to answer, and then we'll look at number 4 together. So you have plenty of time to answer. And number 4 is actually an extension of number 3, because if the graph is telling you as volume goes down, pressure goes up, as temperature goes up, pressure goes up, then that is the relationship between pressure and volume, between temperature and pressure, and between moles. Okay, so number 3 and number 4 are very, very similar questions, because what the graph tells you is the relationship. All right. And then that leaves us with number 5, which is the last question. The last question. What observations can you make about gases from the simulation? I'm expecting you to list 3 of them. So if we go back to the simulation, we could reset this. And question 4. Okay, let's go back. He says he doesn't understand question 4. If we look, 3 and 4 are essentially the same question. They're just worded in a very different way. This one tells you to create the graph. Okay, and then it asks you, what is the graph telling you? So what conclusion can you draw from the graph? Graphs tell us relationships. So what is the relationship between pressure and volume? If we go back to our graphs, pressure and volume, here is our relationship. Exactly what the graph told us is our relationship. So we're really practicing kind of answering graph questions with that one. It's the same answers. You just write them 2 times. You could if you wanted to, I guess. The difference would be if you were writing it, you would say the relationship between would be. All right, so observations that you can make about gases from the simulation. Well, there's a few things that we can look at. We could go ahead and give us all of our information that we have. We could add some gas. All right. You're going to have to answer these on your own, but you have to have 3. So if we look at the movement, do you notice anything specific about the movement of gas molecules? Okay, so there's no set pattern. What we might notice is let's follow 1. Notice it goes in a straight line until it hits something else. That's an important observation to make. So if we follow 1 atom, it's going to go in a straight line until it hits something else. There, it hit something. Our little atom friend. Oh, it hit something. So there's no specific direction it's going to go. It's kind of like if you were at a pool table, they're going to go all different directions when they make a collision. There's one observation. Yeah, they go in a straight line until they hit something. When I heat gas molecules, look at this. Look at the speed. What happens to the speed of those molecules? We could even, if we started to count the wall collisions for the sample period is picoseconds, 388 wall collisions. Well, what happens if I cool down my temperature? Notice that temperature goes down, pressure goes down, so we see that relationship in action again. Now, if I have a much cooler temperature and I count wall collisions, what am I going to get? A lower number. At a cooler temperature, there's less pressure, there's less collisions. Okay. There's another observation. What other observations could we make? Maybe if we switch to light particles, do they behave differently? We'll put all of our measurements back on there. Let's put some light particles, so lower mass particles, and let's see what they say. Seems like they're moving a little faster, but let's cool them down. See if they slow down when we cool them down. Yeah, they do slow down when we cool them down, just like the heavier particles. Let's try to follow one of them. They still go in a straight line until they hit something else. Right, so the lighter particles and the heavier particles behave in the same way. That's another observation that you could write down. All right, so at this point, you should have enough to go ahead and submit those. Like I said, you might want to wait to start the CK12 until we actually teach the gas laws. That way you have a good foundation for it. Please make sure that you have this submitted and that you are caught up to the gas laws assignment. So some of you still need to work in balancing chemical equations.